In this lecture, we discuss about the application of integration. This is basically chapter 6, and we have to discuss only the section 6.1, which is related to area between the curves. In chapter 5, we define and calculated areas of a region that lies under the graphs of a function. Here we use integral to find areas of a region that lies between the graph of two functions. Let us consider a region S between the two curves y is equal to f of x and y is equal to g of x, and between the vertical line, this is x is equal to a, this is one vertical line, and the other side x is equal to b as another vertical line. Now let f of x is greater or equal to g of x, because the graph of this function lies above the x-axis and this lies below the x-axis. So let this f of x is greater or equal to g of x in the interval from a to b, and both functions are continuous. So this is the basic condition that both of these functions f of x and g of x are continuous functions. You know, and already we discussed about area under the curve of a single function y is equal to f like this. We divide this region in n steps of equal width, and we approximate the ith step by a rectangle with base delta x like that, and the height f of xi minus gxi star. So let this is the ith simple point xi, and the area of this, the width of this rectangle is delta x. Now here this is f of x I star, the value of a function at this point, and g into xi star is the value of this function at xi star. So this height of this function is equal to f of xi star minus gi star, where xi star represent the sample point. And then this we can divide into n sample points xi, x1 star, x2 star, and n2 xn star. And then according to the Riemann sum, because we apply the Riemann sum to find the area of this region S. So according to the Riemann sum, the area is equal to f of x summation of from 1 to n f of xi star minus g xi star into delta x. This approximation appears to become better and better as n approaches to infinity. This means that if we divide this region into infinite number of steps, then we get better result and the error will be reduces in this case. Therefore, we define the area A of a region S as the limiting value of the sum of the area of the approximate integral. This is already discussed in the previous lecture, and basic of Riemann sum. So this area is given by a is equal to and limit n tend to infinity. I is running from 1 to n f of xi star minus g of x star into delta x. The area A of the region bounded by the curve y is equal to f of x, y is equal to g of x, and the vertical line x is equal to a, x equal to b, where f and g are continuous, and f of x is greater or equal to g of x. There is a possibility that f of x is equal to g of x. Both of these functions are equal. The curve of these functions are equal in the given interval, which is a to b, and this is equal to, according to the Riemann sum, that this is equal to the integral of having limit from a to b f of x minus g of x into d of x. So this is the sample formula for the to find the area between the two bounded by the two curves and between the two vertical lines. Also, it is important to mention here that for g of x is equal to 0, if this g of x is 0, it is a special case where S is the region under the graph of f. So our previous definition of area has been recovered. So previously we discussed that the area is equal to integral from a to b f of x and to d of x, but here two function, the area between bounded between the two function, so that is the this is the that area, the definition of that area for a single function as a special case of this definition of area between the two curves. In the case where f and both are positive, you can see from the figure 3, if both functions are positive, because this f of x and g of x are lies in the first quadrant, and this shows that this f of x and g of x both are positive. So you can see from figure 3, and we can write this area a is equal to area under the curve y is equal to f of x, this one, minus time the area under the curve y is equal to g of x. This means that this area under the curve from here to here, and this is g of x, so area under the curve from here to x-axis bounded and the bounded by the vertical line x equal to a and x equal to b. So in the mathematical form we can write this is area under the curve y is equal to f of x. So this we can write integral from a to b f of x d of x minus, and this we can write in the mathematical form, that integral from a to b g of x into d of x. So taking this integral common, so this will be equal to, this is a integral from a to b f of x minus g of x into d of x. So for both positive function we can use the same formula. For example, area find the area of the region bounded above by y is equal to e to power x, bounded below by y is equal to x, and bounded on the sides by x is equal to 0 and x is equal to 1. So this is the this is the equation of vertical line x is equal to 0. So this is x is equal to 0 is this line, and x is equal to 1 is equal to this line, and y is equal to x is something straight line, so this is y is equal to x, and the graph of y is equal to e to power x is this one, y is equal to e to power x is exponential behavior. Solution, the region shown in figure 4, the upper boundary curves y is equal to e to power x, this is given bounded above. So the upper boundary curve is represented by y is equal to e to power x, and the lower curve boundaries as is equal to y is equal to x. So we use the area formula to, with f of x is equal to e to power x and g of x, because this is lower boundary, so we can write this g of x is equal to x, and here this is given x is equal to 0 and x is equal to 1. So this is basically x is equal to a and x is equal to b, so a is equal to 0 and b is equal to 1. So using the formula, area a is equal to this one. Now using just putting the value of a is equal to 0, b is equal to 1 over here. So this is integral from 0 to 1, and this is f of x, which is e to power x, and this is g of x, which is equal to x dx. So by integrating this function, integral of e to power x is e to power x, and the integral of x square as x square by 2, and these are the limit of this integration. Now then, using the fundamental theorem of calculus, that upper limit using putting the values and this integrated function and this and upper limit minus lower limit. So insert x is equal to 1 first, and then minus using x is equal to 0. So x e to power 0 as 1, and x is equal to 0 as 0. So this is minus time 1. So now simplify more this term. So e is equal to minus 1.5. This is the area of the region bounded by these two functions. In general, when we set up an integral for an area, it is helpful to sketch the region to identify the top curve y of t. It is that just for the simplicity we can represent this curve y of t. The top curve is represent the top curve. So y is a curve and t is the top curve. So this we can represent this is yt. The bottom curve yb can be represented by yb. B represent the bottom, and the typical approximating rectangle as shown in the figure 5. You can see this this is the yt upper curve, top curve, and this is yb, this is bottom curve. So then the area of the typical rectangle is yt minus yb delta x. So this is basically the height which we represent in the previous example is f of xi star minus g of xi star. So here we can write in simple form that yt minus yb, where yt represent the top curve and yb represent the bottom curve. And the width of this rectangle, this is rectangle strip, which is equal to delta x. So what is the area of this rectangle strip, which is equal to yt minus yb times delta x? So that is the area of this rectangle. And the equation a is equal to this one. So this is yt minus yb delta x. And according to the Riemann sum, this is equal to, when we divide this region S into infinite number of steps, so then we can write integral from a to b. Then the area of this region is equal to integral a to b yt minus yb into d of x. This is the previous formula, but just representing f of xi by yt and g of xi by yb. So this is AG notation we can write and this use for the next example. Also, you can see from these figure, this is figure 2 and this is figure 3, let's suppose. So notice that in this figure the left hand boundary reduced to a point. This is the left hand boundary of this region. So this is a point because they coincide with each other, they cross each other, these curves. And from this figure, also from this figure, the right hand boundary, this is the right hand boundary reduced to a point. Now if both boundaries, if there is a situation where both boundaries, this boundaries and this boundary as well, both boundaries are reduced to a point, then we have to find x is equal to a and x equal to b first. This means that we we are not given that x is equal to something, x is equal to b. So if both boundaries are reduced to a point, then first we have to find the vertical line x is equal to a and x is equal to b. This means sample mean that the point of interaction. So this is the point of interaction of these top and bottom curves. This is the top. This is the point of interaction of this top and bottom curve. So for this, we have to firstly determine the vertical line x is equal to a and x equal to b. For example, find the area of region enclosed by the parabola y is equal to x square and y is equal to 2x minus y square. So both of these are the equation of parabolas because the highest degree of this equation is 2, and here again the highest degree of this equation is 2. So here you notice that there is no boundaries. There is no vertical line x is equal to a, x is equal to b, because we need the lower limit of integral and upper limit of integral a and b, then we can calculate the area. So the first we first find the point of interaction of the parabolas by solving their equations simultaneously. So for this you have to solve these two equations of the parabolas. So put y is equal to x square, we are here over here. So this will be x square is equal to 2x minus x square. So this one x square is equal to 2x minus x square, or we can write 2x. So in 2x square minus 2x is equal to 0 from here. And so from here, common 2x, 2x. So this will be equal to x minus 1 is equal to 0. And from here we can write this x is equal to 0 and x is equal to 1. So x is equal to 0 and x is equal to 1 are the two roots of this equation. Now we have to find the point of contact. This is the point of contact of these curves. This is the upper yt, this is the upper curve 2x minus x square, and this is the bottom curve yb, which is x square. So when x is equal to 0, then y is equal to 0. This means that y is equal to 0, and when x is equal to 1, then y is equal to, put here x is equal to 1, then y is equal to 1. So this means that when x is equal to 0, then y is equal to 0. So one point of contact is 0, 0, which is the origin, and you can see from here. And when y is equal to, when x is equal to 1, then y is equal to 0. So we can write in the interval in the other way. When x is equal to 1, then y is equal to 1. So this is the another contact point of this parabolas. Now, so from here x is equal to, a is equal to 0, and from here we can write this is b, which is equal to 1. And we see from the figure 6 that the top and bottom boundaries are, this is the top boundary and this is the bottom boundary. Now the area of the typical rectangle is equal to, this is the some typical integral delta x, and this is equal to a top boundary minus top curve minus bottom curve. So this is yt minus yb delta x, and this we can write yt, which is equal to 2x minus x square, and yb is x square, y is equal to x square. So this is x square into delta of x. And the region lies between the x is equal to 0 and x is equal to 1, because we already find this the point of contact. So from here we can say this region lie between the x is equal to 0 and x is equal to 1, because this is the region. So this region lies between x is equal to 0 and x is equal to and 1. This is x is equal to 1. This we concluded from here by solving these two equations simultaneously. So the total area is represented by a is equal to from 0 to 1. This is 0 to 1 because a is equal to 0, b is equal to 1. And right, we can write this is 2x minus 2x square. So this is 2x minus 2x square dx. So this is equal to 2 times 2 come out here commonly. So this is 0 to 1 x minus x square into dx. By integrating this 3 by this one, integration of this x is x square by 2, and this is minus x cube by 3, and the limit from 0 to 1. Now using the fundamental theorem of calculus, so we can write this is upper limit minus lower limit. So simplify this thing, which is equal to 1 by 3. So total area, the area bounded by the parabolas as equal to 1 by 3. If we are asked to find the area between the curve y is equal to f of x and y is equal to g of x, where f of x is greater or equal to g of x for some value of x, so you can see that this is here in this region, in the interval a to b, f of x is uh, f of x is greater or equal to g of x. But here in this interval, in this region S2, y is equal to g. This is y is equal to g of x. This is the curve of g of x, and this is the curve of f of x. So here g of x is greater or equal to f of x. And again in the region third x3, here f of x is, this is f of x. So f of x is greater than g of x, because this is the g of x. This is the bounded above and this is bounded below curve. So f of x is greater than g of x. So in situation like that, f uh, we have to find the area, the curve between the curve y is equal to f of x and y is equal to g of x, where f of x is greater or equal to g of x for some value of x, but g of x is greater or equal to f of x for other value of x in the interval. Then we split the given region S into several regions like S1, S2, and S3 with areas. We calculate the areas of these individual regions, which is A1, A2, and A3, and so on, as shown in the figure 11. You can see here. We then define the area of region S to be the sum of the areas of the smaller region S1, S2. That is, this means that we can total these, sum these region, the area of these region. This will give the total area A, which is equal to A1, A2, and so on. To analyze this figure, we can see that f of x, because the area is positive, so therefore we can write the absolute of f of x minus g of x. So this is f of x minus g of x when f of x is greater or equal to g of x. This mean this means that f of x here in this rectangle is in this region S1, f of x is greater or equal to g of x. Again in the region S3, f of x is greater or equal to g of x. And the region S2, g of x minus f of x. Just the order of the function is reversed. So this is g of x minus f of x when g of x is greater or equal to f of x. So in this case, g of x, which is this one, the curve of g of x is that g of x is greater or equal to f of x. So we can split the area of this the region and to sum of some region, and then we convert it to the sum of the region of the individual, sum of the areas of the individual region. We have the following expression for the area of region like that the area between the curve y is equal to f of x and y is equal to g of x, and between x is equal to a, which is the vertical line, and x is equal to b, as given by area is equal to from a to b, integral from a to b, f of x minus g of x absolute into d of x. So you have to divide this region, the region into some sum of region, and then you can calculate the individual area. For example, find the area of a region bounded by the curve y is equal to sine of x and y is equal to cos of x. At x is equal to 0 in the region, in the interval x is equal to 0 and x is equal to pi over 2. So the solution of this, the point of intersection occur when sine of x is equal to a cos of x, that is when x is equal to pi by 4, because the value of this function x is equal to cos of x and sine of x is equal to 1 by 2 when 1 by under root 2 when x is equal to pi by 4. So this means that the interaction of these two curves occur at a point x is equal to pi by 4. The region is sketched in figure 12. This is the region. So This is the region for the cos. This is the graph of cos of x, because when cos x is equal to 0, cos is equal to 1, and when x is equal to 0, the sine is 0. So this is the region. So in this region, 0 to 4 by pi, and from 4 by 5 by 4 to 5 by 2, in this region, this f of x is greater or equal to g of x. And after this interval, pi by 4 to 5 by 2, 5 by 2, in this region, region S2, the g of x, which is y is equal to sine of x, is greater or equal to f of x, which is x is equal to sine cos of x, y is equal to cos of x. So this means that, and this is the boundaries, x is equal to 0, this is given, and x is equal to pi by 2. So we can write this x is equal to 0, and here x is equal to pi by 2. Observe that cos of x is greater or equal to sine of x in the given interval 0 to in the domain x is equal to x is greater or equal to 0 less or equal to pi by 4, and sine of x is greater or equal to cos of, because the graph is this is upper bounded and this is the lower bounded in this interval. When x is greater or equal to pi by 4, this one, and less or equal to pi by 2, therefore the required area is equal to 0 to pi by 2. So this is limit of integration as 0 from 0 to pi by, the total area is the limit of this integral from 0 to pi by 2, and then we split this region to two regions. So 0, so the integral, so this is equal to 0 to pi by 4, and this is f of x, which is cos of x, and this is g of x, which is sine of x dx. So this is area a1 and plus a2. These are denoted these region, two regions, so we denote this area of region 1 as s1 as a1, and the area of region 2 as s2, which is a2. So we split this region. This is the absolute of the integrand, so we can split the region 0 to pi by 4, 0 to pi by 4. This is cos of x minus sine of x plus, and this is from pi by 4 to pi by 2. We can write first sine of x and then cos of x, and here we can write cos of x minus sine of x, cos first and then second, because this is the top curve and this is the bottom curve in this interval 0 to pi by 4. You can see here 0 to pi by 4. So now just taking the integration of this, cos of x is sine of x, and the integral of sine is minus cos of x, and then using the fundamental theorem of calculus we get the area. So this is sine of x, and integral of sine is minus cos of x, so minus, when minus will be equal to plus, and these are the limit of the integration. And again, this is the integration of cos is sine is minus cos, and cos is sine of x, and these are the limit of integration. So using the fundamental of theorem of calculus, upper limit minus lower limit, so we can write this is pi by 4. So sine pi by 4, cos pi by 4, and sine pi by 4 is equal to 1 over under root 2, and sine cos pi by 2 is 0, and sine pi by 2 is 1, and minus time cos pi by 2 is 1 under root 2, and sine pi by 2 pi by 4 is again 1 over under root 4. So simplify these things, so which is equal to, this is the area of 2 and 2 under root 2 minus 2 times. And this particular example, we could have saved some work by noticing that the region is symmetric about x equal to pi by 4. In this one, in this graph, you can see this is the region is symmetric between this point x is equal to pi by 4, because this region and these region are equal, and these are symmetric. The shape of these regions are similar, so we can use this fact that area is equal to 2 times a1. This is equal to 2 times a1, because you calculate the area of region 1, then multiply 2 with this region 1, then we get the total area of the region. So this is 0 to pi by 4 cos of x minus sine of x into dx. We can write in this form the answer of this, and this answer is same. Some regions are best treated by regarding x as a function of y. If region is bounded by curves with the equation x is equal to f of y, sometimes we can write in this form x is equal to f of y. In previous example, in the previous sections, we can write y is equal to f of x. But here, if we can write some region is easily calculated, the area of that region, it can be easily calculated. If you can write this function x is equal to f of y, mean x is a function of y, and x is equal to g of y, where y is equal to c and y is equal to d, where f and g are continuous and f of y is greater or equal to g of y. For this region, you can see from figure, see this, we can write x equal to g of, this is a curve in this form, in the vertical form, and y is equal to d, this is the horizontal line, c is equal to y is equal to c, these are the horizontal line. And this is the delta y is the width of this region, and this is the function f of x is equal to g of y and x is equal to f of y. So the length of this rectangular strip is equal to f of y minus g of y, final from initial. So the area of this region is a is equal to c to d, from this c to d, f of y minus g of y. If we write instead of f of y and g of y, we represent this in the other notation, that xr for the right boundary, or this is xr, r represent the right, and xl, this is xl represent the left boundary, or the left boundary. Then as shown in figure 14 illustrates, we have a is equal to c to d, we can write this is in the form of, this is the right boundary, so we write xr minus, and this is the xl dy. So you know that these are the function of y, g is again a function of y, so we can write here this is dy. If this is a function of x, then we can write dx. So the general form of this, in this case, the area is equal to c to d into xr minus xl dy. Here, a typical approximating rectangle has dimension xr minus xl. So the dimension of this typical rectangle, this small rectangle, is xr minus xl, and we can write here, this is the length of this typical integral, this small rectangle, as xr minus xl. That is, we can write in this form, this is xr minus xl, and this is delta y. Example 7, find the area enclosed by the line y is equal to x minus 1, which is a straight line, and the parabola y square is equal to 2x plus 1. So by solving these two equations, we find that the point of intersection are, you have to solve these two equations simultaneously. Just put y is equal to x minus 1 over here. So then open this square, x minus 1 whole square, and then you simplify. So we get the values of x as I discussed in the previous example. So firstly, you have to find the point of interaction of these two curves uh, by solving these curves simultaneously. So we solve this equation of the parabola for x, and notice from the figure 15 that this is figure 15, and these are the minus 1 and minus 2. This is minus 1 and minus 2. Y is equal to x minus 1. This is a straight line. You can sketch easily this graph. This is the right shift from x equal to minus 1. So this is the graph of this function, and this is the parabola. So the graph of parabola, and this parabola is open to the positive x-axis, so we can write this in the form. And -1, -2, these are the interacting point, and 4 and 5 is again interacting point of this. So xl is equal to, from here, this curve we can write in the form of this one. So find here x from this. So x is equal to 1 by 2 y square minus 3. So shift here minus 6, and then from here x is equal to, so this curve will be shifted to x is equal to y plus 1 if we shift minus 1 over here. So this is xr is equal to y plus 1. So this is the left curve, and this is the right curve. Now we must integrate between the appropriate y values. Y is equal to -2 and y is equal to 4. The question arises that how you select this is y is equal to from these points. From these point of interaction, you have to choose the y is equal to -2, because now we are integrating this area with respect to y. So therefore we choose this is the lower integral -2, the lower value, and this is the upper value, the highest value, which is 4. Therefore we write y is equal to -2 and y is equal to 4. So basically this is the value which is c, y is equal to c, and this is the y is equal to d. So c is equal to -2 and y is equal, and d is equal to 4. So thus we can write in the integral form area a is equal to -2 to 4, and this is equal to xr minus xl, right boundary, right curve minus left curve, into dy. Now using the values of xr and xl, this one from here, and then simplify this and integrate. And so we simplify this is equal to -1 by 2y square plus y plus 4 into dy. And then we integrate this with respect to y, and then using the fundamental theorem of calculus. So this is basically the definite integral, upper limit minus lower limit, and simplify, we get this is equal to 18. So area of this region is equal to 18. You have to solve some related questions in the exercise 6.1. The next topic is this is from chapter 4, section 4.4, the indeterminate form and L'Hopital rules. The indeterminate form and L'Hopital rules. Suppose we are trying to analyze the behavior of the function f of x is equal to ln of x divided by x minus 1. We know that this function f is not defined at x is equal to 1, because at x is equal to 1, ln of 1 is 0, and here 1 minus 1 is 0, so we'll get 0 by 0 form. So we are trying to analyze the behavior of this function near x is equal to 1. So we need to know how f behaves near n is equal to 1. In particular, we like to know the values of the limit x approaches to 1, ln of x divided by x minus 1. In general, if we have limit of the function, so we have to find the limit of this function. For this, we cannot use the this is 0 by 0 form. So sometimes we have to remove the 0 by 0 form by friction, by using the we remove this 0 by 0 form by using some sine of x divided by x and limit x approaches to 0. This theorem is equal to 1. And sometimes we use the factorization factorize this term and cancel out the common term, common factor, and then we get the limit of that point, that function. And sometimes we have to rationalize the function, and then we apply the limit, we get some limiting value of that function. But here the case that this is not a polynomial. In case of rational function, we can rationalize, we can factorize or take common some factors, and this cancel out these factors, and we get the value of that function as a limiting value. But here this is not the case, that this is not a rational function, this is ln of x. So there is no way to calculate the limit of this function. In general, we can say we have a limit of the form limit x approaches to a f of x by g of x, where both f of x approaches to 0 and g of x approaches to 0, as in the previous case 1, that x is, when x is equal approaches to 1, then the this f of x approaches to 0 and g of x is again approaches to 0. Then this limit may or may not exist, and it is called the indeterminate form of the type 0 by 0, because by applying this limit we get 0 by 0 form, which is known as the indeterminate form of type 0 by 0. We made some limit of this type in chapter 2. Another situation in which a limit is not obvious occur when we look for a horizontal asymptote of f and need to evaluate the limit. When we to calculate the horizontal asymptote, then we apply the limit x approaches to infinity and minus infinity. And if you apply the infinity on this function, so ln of infinity is ln of infinity is equal to infinity, and this is infinity minus 1 is again, this is infinity minus infinity, this infinity form, infinity by infinity form. This form is again known as the indeterminate form. In general, we can it is not obvious how to evaluate this limit, because both the numerator and denominator become large when x approaches to infinity. Because this is a large and this is large, so both numerator and denominator become very large. So there is a struggle between the numerator and denominator. If the numerator wins, the limit will be infinity. If the numerator win, then this will be infinity, and here will be some value. So dividing infinity by some value is equal to infinity. This means that the limit of this function will be equal to infinity. The numerator was increasing significantly. In other words, we can say that the numerator was increasing, this numerator was increasing significantly faster than the denominator. If the denominator wins, mean the denominator increasing significantly faster than the numerator, then the answer will be equal to 0, because here will be 0 and here will be infinity. So anything by 0 is equal to 0 by infinity is equal to 0. Or there may be some compromise, in which case the answer will some finite positive number. In general, limit of such type we can write, if we have a limit of the form limit x approaches to a f of x by g of x. For example, this is the limit x square minus 1 to x square plus 1. So we can write the highest power in the denominator as a common. So taking x square common, because by directly applying the limit, we get infinity by infinity form. So this is we already we tackle such type of limit in the previous chapter, chapter 2 especially. So by taking x square common from denominator, we have to the form, this is 1 minus 1 over x square, and this is 2 plus 1 divided by x square, and x square term are cancelled out from here and here. So now applying the limits, we get 1 minus 1 over infinity, and 1 over infinity is obviously this is equal to 0, and 1 over infinity again here 0. So this is 1 by 2. So the limit of this, we can calculate the rational function. This is the rational function. The limit when x approaches to infinity, we evaluate this limit, and which is equal to 1 by 2. But this method does not work for a limit such as 2 by L'Hopital rule also applies to this type of indeterminate form. What is L'Hopital rules? Let's define it. Suppose f and g are differentiable and g prime derivative of g of x is not equal to 0 in an open interval I that contain a expect possibly at a. Suppose that the limit when x approaches to a is f of x is 0 and g of x is also 0, or the limit of this function is plus infinity minus infinity, and the g of x is also plus infinity and minus infinity. In other words, we can say that we have an indeterminate form of the type 0 by 0 or infinity by infinity form. Then the limit x approaches to a f of x by g of x is equal to, this limit is equal to the derivative, the individual derivative of this function f of x, f prime of x, and the derivative of this function g of x. So these both limit are equal. This is the basics, this is the concept of L'Hopital rule. If the limit on the right side exists or infinity and minus infinity, if this exists, this will be finite value, and this is also exist if this limit gives minus infinity or infinity, but only the form as 0 by 0, infinity by infinity is the indeterminate form. Minus infinity and plus infinity, these are not indeterminate form. We already discussed about that. This is the limit exists, and these are the for the horizontal and vertical asymptote. Some notes over here. L'Hopital rules says that the limit of the quotient of the function is equal to the limit of the quotient of their derivative, provided that the given condition are satisfied. The given condition is that the 0 by 0 form and f and g are continuous functions. L'Hopital rule is also valid for one-sided limit. You can also apply for the one-sided limit, and for the limit at infinity or negative infinity, that is x approaches to a, can be replaced by any of the symbol x approaches to a plus limit from the right side, from the left side, or extending to infinity or approaches to minus infinity. For example, you have to find the limit of this function when x approaches to 1, ln of x divided by x minus 1. So in this case, if we directly apply the limit, when you apply the limit on this numerator f of x, this will give ln of 1, and we know ln of 1 is equal to 0. And using the limit, applying the limit on this denominator function, which is g of x, so this will be equal to 0. This means that we get 0 by 0 form. So directly applying limit on this function gives the 0 by 0 form, and this is the indeterminate form of type 0 by 0. So we can apply the L'Hopital rule here. So L'Hopital rule is basically this is equal to limit x approaches to 1 and derivative of this function, and then the derivative of the denominator function. So derivative of ln of x is 1 by x, and the derivative of this one is 1. Now this will be equal to 1 by x. So just applying the limit 1 over x. So 1 by 1 is equal to 1. So the limit in this case exists. Another example, calculate the limit e to power x divided by x square when x approaches to infinity. Then we have limit x approaches to infinity, e to power x is equal to infinity, because e to power infinity is equal to infinity, and limit x approaches to infinity, x square is equal to infinity. So the limit is in the indeterminate form of type infinity by infinity, because by directly applying the limit, you get infinity by infinity form. So then we use the L'Hopital rule in this case again. So we can write this limit x approaches to infinity, and this is equal to derivative of this and derivative of this denominator function. So derivative of e to the power x is e to the power x, and derivative of x square is 2x. Now applying the infinity, applying the limit, on this function. So when x approaches to infinity, e to the power x is again approaches to infinity, and here if you apply the limit, so again limit x approaches to infinity, this will be approaches to infinity. This means that again we get infinity by infinity form if we apply the directly the limit on this function. So we again use the L'Hopital rule. We have to practice these rule up to that the 0 by 0 form or indeterminate form is vanishes. Again using the L'Hopital rule over here. So this will be derivative of this function as e to the power x, which is e to the power x, and the derivative of this function as 2. So this we can write in this form too. Now applying the limit. So limit of e to the power x is e to the power infinity divided by 2, and this will be equal to e to the power infinity is basically infinity, and this is 2. So infinity divided by some number is equal to infinity. So we remove with the L'Hopital rule the indeterminate form. Example 3, you can calculate this is when applying the infinity, ln of infinity is infinity, and the denominator, this is square root function. So applying when x approaches to infinity, this is infinity by infinity form. So again using just the L'Hopital rule. Example 4, find the limit when x approaches to 0 tangent x minus x divided by x cube. So nothing that both tangent of x minus x approaches to 0 when x, because tangent 0 is 0 and x is 0, 0 minus 0 is 0, and in the denominator also x, so x by 0 form. So by directly applying the limit, we get the 0 by 0 form. So therefore we use the L'Hopital rule. So take the derivative of this function. So derivative of tangent is equal to secant square x, and derivative of x is 1, and the derivative of this function denominator function is 3x square. Now since the limit on the right hand side is still indeterminate type, by applying the limit directly, so this will be secant square, 0 is 1, 1 minus 1 is 0, and here 0. So again we get, by applying the limit to here in this function, we get again 0 by 0 form. So to remove this indeterminate form, we use the L'Hopital rule again. So derivative of secant square is secant square into tangent x. So derivative of the secant square as is 2 secant secant x tangent x, 2 secant x using the power rule is the derivative of this one. Derivative of secant square x is basically 2 secant x into tangent x, and 2 secant x, and the derivative of tangent using power rule. So this is 2 secant x, and derivative of secant is secant into secant x into tangent x. So this will be equal to secant, 1 secant and 1 secant. So this will be secant square into tangent x. So this will be, and the derivative of this constant is 0. So this is 2 secant x square tangent x divided by derivative of this is 6x. But limit x approaches to 0, again this is equal to 1. So we simplify the calculation by writing 2 secant square tangent x, which is equal to applying the limit on this vector, this one, and then applying the limit on this tangent x, and this is 1 by 3, this is cancelled out. So the limit of this function, limit x approaches to 0 secant, is equal to 1, because this is 1 by cos and 1 by cos 0 is 1, so 1 by 1 is again 1, and the limit of this tangent x for x, this is 1 by 3, and the limit of this is 1. So 1 time this limit, which is equal to 1 by 3, limit x approaches to 0, tangent x over x. Now again, if we use the we apply the limit on this function, so this will be tangent 0 is 0 and this is 0 again, we get 0 by 0 form. This is the third time we get 0 by 0 form. So again, using the L'Hopital rule, so derivative of tangent as this is 1 by 3, limit x approaches to 0, derivative of tangent as secant square, and derivative of this x is 1. Now applying the limit x approaches to 0, so secant square x 0 is 1, so 1 by 1 is 1, and this is multiplied with 1 by 3, so the limit of this function is 1 by 3. So in this example, we use the L'Hopital rule 3 times. Another indeterminate form product, if limit x approaches to a, f of x is equal to 0, and limit x approaches to a, g of x is equal to infinity or minus infinity. If we apply the limit and we get the form like that, then it is not clear what the value of limit x approaches to f of x and g of x when x approaches to some finite value. If any will be, there is a struggle between f and g. If f wins, then the answer will be 0. If g wins, the answer will be infinity or minus infinity. This is the comparison of these two functions, that faster, which one function is faster and significantly increasing. Now, there may be a compromise where the answer is finite non-zero number. This kind of limit is called the indeterminate form of type 0 time infinity, and we can deal with it by writing the product of f and g as a quotient. So we can write this is f divided by 1 over g, and we can write this is g divided by 1 over f. So we convert the product of two functions to quotient of two functions. Then we get 0 by 0 or infinity by infinity form, and then we use the L'Hopital rule, because we convert this function, this form 0 to infinity form to 0 by 0 or infinity by infinity form, and we know that the 0 by 0 and infinity by infinity form can be handled by the L'Hopital rule. Example 6, evaluate this limit x approaches to 0 from the right side x ln of x. Now if you see, if we apply the limit directly, so this will be equal to 0 time ln of 0. So we know that 0 time and ln of 0 is equal to infinity. So this is, so we get the indeterminate form of the type 0 to 0 time infinity. So for this we can write that we convert this into, this is the product of two function, which is polynomial and logarithmic function. So we convert this product into quotient of these functions. So you can see the given limit is indeterminate, because as x approaches to 0, the first factor x approaches to 0, this one, and that's while the second factor ln of x approaches to minus infinity. Oh, okay. So this is x approaches from the left side, so this will be minus infinity. We can write x in the form 1 by x, 1 by 1 over x, and we have 1 over x approaches to infinity as x approaches to 0. So we can write in summary of these sentences are, we can write this in the form of quotient. So this is ln of x, and we can write this x in the form of 1 by x. So this is equal to limit x approaches to 0 from the right side, the derivative. Now here, if we apply the limit directly, we get, this is the ln of we get ln of 0. Ln of 0 is infinity, and 1 by 0 is again infinity. So this is the indeterminate form of infinity by infinity. Now we can use the L'Hopital rule to remove this indeterminate form. So By taking the derivative of this function, we get this is 1 by x, and divided by the derivative of this, derivative of 1 by x, derivative of 1 by x is basically equal to minus 1 by x square. So this is minus 1 by x square. Now cancel out this term and we get this is minus x. Now applying the limit, we get the limit of this function as 0. So this means here again the L'Hopital rule works for the in the finding of the limit of this function. Another form, indeterminate difference. If limit x approaches to f of x equal to infinity and limit x approaches to g of x is infinity, and there's the difference of these two limits, these two functions, you have to calculate the limit of this, find the limit of x approaches to a f of x minus g of x. There is difference of these two functions. It's called the indeterminate form of type infinity minus infinity. So this is another type. Again, there is a contest between f and g, where the answer will be infinity if f1, or will be minus infinity if g, when f is vanishes, then the answer will be minus infinity. If g is vanishes 0, then the answer will be plus infinity. Or will they compromise on the finite number? Or there may be possibility that the limit of this function is equal to some finite number. To find out, we try to convert the difference into quotient, for instance by using the common denominator or rationalization, or factoring out the common factor, so that we have an indeterminate form of type 0 by 0 or infinity by infinity. So in this difference case, infinity minus infinity form, we try to convert the difference into quotient. Maybe there is some possibility that we convert this difference into quotient, or the common denominator. Some we can take some common from these two functions, we get a common denominator, or we rationalize this function, or factoring out a common factor, and then this will be converted to 0 by 0 or infinity by infinity form, and then we use the L'Hopital, utilize the L'Hopital rule for finding the limit of this type of functions. For example, when compute the limit of this, limit x approaches to 1, 1 by ln of x minus 1. So by directly applying the limit, so by directly applying the limit, this will be 1 over ln of 1 over ln of 1, and we know ln of 1, this is minus 1 over 1 minus 1. So this will be equal to 1 over ln of 1 is 0, and this is 1 minus 1 is 0, so 1 by 0, and this will be equal to infinity minus infinity type. This is again another indeterminate type like that. So in this case, the first note is there, this one. So the limit is indeterminate type of infinity minus infinity. Here we can start with the common denominator. We can take the LCM of this. So this will be equal to LCM of this ln of x and 2 x minus 1, that is x minus 1 and 2 ln of x. And we can write here this function here, and over here this is x minus 1. So just taking the LCM of this function, we get this form x minus 1 minus ln of x, and divided by x minus 1 into ln of x. Both numerator and denominator have limit of 0, so L'Hopital rule applies. Because now if here you applying the limit, this will be 1 minus 1 is 0, and this is 1 minus 1 is, and minus ln of 0 is ln of 1 is 0, divided by 1 minus 1 is 0. So this will be equal to 0 by 0 form. So now we can use the L'Hopital rule. So we converting this this function, this difference of function to a common denominator. This is the common denominator of these two functions. And now we get this type 0 by 0 form. So using the L'Hopital rule now. So taking the derivative of this function and the denominator function. So derivative of this function is 1 minus 1 over x, and using the product rule here, that the derivative of this function is x minus 1, and the derivative of ln of x is 1 by x, and derivative of x minus 1 is 1, and ln of x is as it is. So using the product rule here. So simplify these things. So this will be limit x approaches to 1, x minus 1 divided by x minus 1 plus x into ln of x. Now using applying the limit, we get applying the limit. So this will be equal to 0, and this is 1 minus 1 is 0, and 1 into ln of this 0 plus 0. So this will be equal to 0, again 0 by 0 form. So again using the L'Hopital rule. So taking the derivative of this one is 1, and derivative of this is 1 plus, and using product rule here because it's a product of polynomial and ln of x. So the derivative of this denominator is equal to this one. Now applying the limit, so this is 2 times, this cancel out. So 1 plus 1 is 2 plus ln of x. Now applying the limit, so ln of 1 is 0, this is 0, and 1 by 2. So the limit of this function is equal to 1 by 2, which is a finite number. And we also mentioned that this limit may be a finite number. Another indeterminate forms, several indeterminate forms arise from the limit when limit x approaches to a f of x raised to the power g of x. For function like that, like x raised to the power ln of x, this is a function f of x, and limit x approaches to 0. So this will be 0 by 0 form. 0 power, no. Here will be 0 raised to the power infinity, because ln of 0 is infinity and x is equal to 0. So 0 raised to the power infinity form. So there are many types of the indeterminate form like this. If this is equal to 0, g is equal to 0, so this will be 0 by 0 form. Here will be infinity raised to the power 0 form, 1k power infinity by 0 form, if the limit of this is 1 and limit of this is plus infinity or minus infinity. So these are also indeterminate form. So to handle these type of indeterminate form, each of these 3 cases can be treated either by taking the natural logarithm, because the property of natural logarithm that this will be come to the base of this the function, or to the product of the function by using the property of the natural log. We can say that let y is equal to f of x to the power g of x in this form, then applying the limit, the natural log on both sides. So this is ln of y, and this is the property of ln of, so this will be g of x and ln of f of x. Or by writing the function as an exponential, so we can write this is another way to represent this is e to the power g of x ln of x, because ln of x and g and e cancel out each other. Ln of x, this is equal to x, because, or we can write x in the form of e is equal to e to the power ln of x, because exponential and logarithmic function are inverse of each other. So this, they will be cancelled out. This will be equal to x. So this is another way to write the form, this function of the form in the form of exponential function e to the power gx ln of f of x. So these are 2 ways. One, to applying the natural log on both sides of the functions, and the second way is to represent a given function in the form of exponential function. Recall that both of these methods were used in the differentiating such functions. In either method, we are lead to the indeterminate form, indeterminate product g of x and to ln of x. This is the product of the intermediate form, indeterminate product, which is of type 0 to infinity, 0 time infinity. And then we divide, when we can calculate the limit of the function in the way that these two functions can be written in the quotient instead of the product of two functions. For example, calculate the limit of this function 1 plus sine 4x raised to the power cotangent of x. So directly applying the limit on this function, this will be sine 0 is 0, so 1 raised to the power cos cotangent of 0 is infinity. So this will be a 1 raised to the power infinity, because when x approaches to 0, the cotangent of x is 0 infinity. So this is the form of 1 raised to the power infinity, and this is the indeterminate form. Solution: first notice that x approaches to 0, so they discuss about this. There's the form of 1, the indeterminate form of type 1, 1 raised to power infinity. So we can write this function. Let's suppose this is equal to y. So y is equal to 1 plus sine 4. Now applying the ln on this natural log on this function both sides. So ln of y is equal to ln of this 1 plus sine 4x cotangent of x. So this will become out here by using the properties of the natural log. So this will be cotangent of x ln of this one. Now by applying the limit, you can see that this is cotangent of 0 as infinity. That is one. And uh, this sine of 0 is 0, so ln of 0 is 0, and ln of 1 is 0. So this is the form infinity times 0, or this is the form 0 to infinity, 0 time infinity. So now we can write this in the division. So now the reciprocal of cotangent is tangent. Cotangent of x is equal to 1 over tangent. So we can write this in this form, and the 1 over tangent. So using this is ln of 1 plus sine 4 of x divided by tangent of x. Now you get the 0 by the, now by applying the limit you can get the 0 by 0 form, because tangent of 0 is 0 and the ln of 1 is 0. So this we get 0 by 0 form. So we convert this form 1 raised to the power infinity and to the form infinity times 0, and then we convert this form to 0 by 0 form. Now we use the L'Hopital rule on this quotient. So L'Hopital rules gives, applying the, just taking the derivative of this one, so it will equal to 4 cos of x divided by 1 plus sine 4 of x, using the definition of the derivative of natural log. And derivative of tangent, we know that this is the secant square x. So this is 4, because cos 0 is 1 and sine 0 1, so 1 by 1, which is 4, and secant of 0 is equal to 1, so 4 divided by 1, which is equal to 4. So this is the finite value in the limit. So far we have computed the limit of ln of y, but what we want to limit of y, to find this we use the fact that y is equal to e to the power ln of y. So this is the another way, another method to find the limit or represent the limit of the type 1 raised to the power infinity in this form, e to the power ln of y, because this cancel out each other. So y is equal to y. So again we can write this is y is equal to e to the power ln of y, and y is equal to what? This is y. So applying the limit when this is 0, so e to the power y, just put the value of y, because y is equal to this thing. So this will be equal to e to power ln of y, which is 1 plus x sine of 4x. So just applying the limit, so this will be the e to power 1 is 0, so this is 4. Just applying the limit ln of 0, so we get e to power 4, which is a constant. And then we can write in the form, so e to power 0 ln of 0 is equal to e to power infinity, e raised to the power infinity. So this is the undetermined form. Okay, so we can write this is by applying the L'Hopital rule. So we get this is the ln of 1 plus cos of 4 of sine 4x, e raised to the power this thing. So this will be reduced to the form e raised to the power 4. And now using again, because y is equal to e to power 4, so we can use that, uh, removing these things. So this will be equal to y is equal to ln of y, this is ln of this thing. So ln of e is equal to, this 4 will come out here, so this is ln of y is equal to 4. So this is the answer like that, ln of y is equal to 4. Also you can calculate or find the limit of this form, find the limit of x raised to power x, just applying the uh, ln of x, ln natural log on both sides, and then the compute the limit of this function. Also you can calculate, you can practice some related question to this topic in the exercise 4.4.